In this lecture, we are beginning our trek down the path of macroscopic understanding by looking at the critical descriptions of matter. We want to define what we mean by matter and then take the time to understand how to quantify matter either by mass or by counting the individual particles that make up the matter. These quantification methods will quickly lead us to the useful concepts of the mole and the conservation of mass. Let's first define what we mean by matter. Matter is stuff that takes up space and has mass. We also acknowledge that matter is made up of very small particles that have mass and take up space. Now, it's nice to have pretty words describing the idea of mass, but it's better if we can see it and measure it, putting a number on it and quantifying it. So how do we measure the amount of matter? There are two ways to do this. We can quantify it by its total mass or by counting the total number of particles within the matter. Of course, you might say, Dr. S., aren't these two ways of quantifying matter connected? Well, yes, they are, brilliant student of mine. But the exact connection cannot be explained without knowing the specific makeup of the particles. That intersection between mass and number of particles will be something we will be sure to look out for as we go along. The matter measurement we are most familiar with is one where we determine the mass by weighing it on a scale or balance. So when I place myself on my bathroom scale and try to measure my weight, am I measuring my mass? Well, the answer is no. Weight is not mass, but then we can also say yes. We can calibrate our instrument, which measures our weight, into a mass value. Let me explain what I mean here. The great Isaac Newton would say we do not measure mass, but the force a body is exerting on the scale. But we usually don't call this measurement our force. We call the force our weight. So how does this force or weight relate to the mass of the body? Well, Newton said the force is mass times acceleration, or F equals ma. Acceleration has the units of distance divided by time squared, or in SI, meters per second squared. So the SI units for force would be mass kilograms times acceleration meters per second squared, giving us kilograms meters per second squared, which is the derived unit called a Newton, after our dear Sir Isaac. But when I'm on my scale, I'm not accelerating or moving. We know that the force that holds us on that scale is a gravitational pull between us and the Earth. So the acceleration value we are talking about here is the gravity, and at sea level is determined to be about 9.80665 meters per second squared, which is not an exact value. The higher in altitude we go, the smaller this gravity value will become, but because of the massive size of the Earth compared to our size, we can treat this as a constant at most normal altitudes. To get even a 1% change in the gravitational acceleration, we would need to be located about 19 to 20 miles above sea level. Bottom line, weight is directly proportional to mass through this F equals ma equation. It seems logical that if we weighed two people on our scale, treating gravity as a constant, that the difference in their weight would be proportional to the difference in their mass. This proportionality makes it easy to build a calibration curve for a scale or balance. Remember, in one of our last lectures when we calibrated the bathroom scale to a set of controls, in actuality, we knew the masses, not the weights, of the controls. So when we calibrated the scale, we converted the weight measured on the scale into units of mass based on the controls. Again, the main reason this works out is because gravity can be considered a constant, and from Newton's equation, F equals ma, or g in this case, the force, or weight, is directly proportional to the mass. What I want you to get out of all of this is that we can be confident that we measure the mass of matter when we read the value on a laboratory scale, since the scale has been calibrated against known masses. As far as the different laboratory scales used in the lab, the most common instruments are either a top-load balance, which is utilized for rough measurements of heavier substances, giving us a precision of plus or minus 1 gram to 0.01 gram, and analytical balances, which are used for highly precise measurements of lighter substances with typical precisions of around plus or minus 0.0001 gram or even smaller. One last thing about mass. Don't forget that the mass is dependent on the volume and density of the matter. The mass is directly dependent on the volume when comparing two different substances that have the same density. The substance with the greater volume will have the greater mass. The mass is directly dependent on the density when comparing two different pieces of matter of the same volume. The matter with the greater density will have the largest mass. We looked at measuring the amount of matter by mass in these last couple of slides. Now let's look at measuring the amount of matter by simply counting the number of particles. The small particles that make up chemical matter can have masses as slight as 1.66 times 10 to the minus 24th grams and be as tiny as 60 picometers or 0.6 angstroms in diameter, where an angstrom is equal to 10 to the minus 10th meters. Because of their tiny size, trying to quantify matter regarding numbers of individual particles would be a pain. It would be much easier to scale this up and maybe count them as a packet or fixed quantity that's easier to manipulate and measure. For example, we typically don't buy or sell individual eggs, but rather you and I would typically buy a carton of 12 eggs, which we call a dozen eggs. Now, if we were transporting a great number of eggs to a grocery store, we would be measuring and counting the eggs by the gross, which is a packet of 144 eggs, which is equivalent to 12 cartons of a dozen eggs. In this same way, we simply scale the large number of particles found in a typical piece of matter in a way that will make it convenient in a laboratory setting to measure, manipulate, and talk about. The number of particles that seem to be convenient is 6.0221413 times 10 to the 23rd particles, which we call an Avogadro's number of particles. It's not an exact value as written, but it is a carefully measured value that we know to quite a few decimals. If we have an Avogadro's number of particles, we say that we have 1 mole of particles. So the conversion ratio we utilize in computing matter is 1 mole of particles equals 6.0221413 times 10 to the 23rd particles. An obvious question would be, where does this funny-looking number come from? Right now, we're not quite ready to get into a rigorous discussion because we need to know something about isotopes. But for now, I can give you a simple rationale. Let's say that the smallest particle we might commonly work with in a chemistry lab is a hydrogen atom, which has a mass of about 1.66 times 10 to the minus 24th grams. Now, if we multiply this mass by an Avogadro's number of the particles, which is equivalent to 1 mole of these particles, then the total weight of these small hydrogen particles would be about 1 gram. This 1 gram mass is easy to measure on a common top load or analytical balance in our laboratories with a high degree of accuracy and precision. By the way, my brilliant student, we just made the connection between mass and the number of particles of the matter. In both cases, we can measure the amount of matter with a scale to get mass. And if we know the average weight of a single particle of that matter, we can easily calculate the number of moles and the number of particles of that piece of matter. In the special case of a closed, isolated system where we contain all the reactants and products of a physical or chemical change, and if we don't measure the mass too precisely, we find that mass will be conserved. This concept was summarized by the great Lavoisier in 1789 when he observed that mass was neither created nor destroyed in a chemical reaction within a closed container using the state-of-the-art balances and scales of his day. Today, we still rely on this limiting case when we do common everyday chemical computations in chemistry. But if the system is different and we were able to measure the mass with a great deal of precision, and I mean a super tiny absolute error, the amount of mass before and after the reaction may not be constant.
Ooh.
The conservation of mass can fail us when we measure the mass of matter before and after a physical or chemical process with this kind of ultra precision and under the right conditions. What was gained or lost that throws off the balance sheet? Well, that would be energy. But again, in regular physical and chemical reactions, the total mass can be considered constant. We'll look more at this idea in greater detail when we talk about energy in another lecture. Well, that's enough for now. See you next time.